Video problem number 53, electronegativity and polarity. Determine if the compounds in video problem number 51 are polar or non-polar. So first, I'm going to show you a trick to determine whether it's polar or non-polar, but this is very important. The trick is not why it's polar or non-polar. So in other words, don't use the trick to ever explain how or why. All right, we'll talk about how or why, but let me show you this. So here's, it's in your notes, but a compound is polar if it has lone pair electrons on the central atom. A compound is polar if it is surrounded by different atoms. Now there are exceptions. We're not going to worry about them until we get to AP. So it's non-polar if it's surrounded by the same atom. Again, this isn't why, this is just how you can tell. And then if there are no lone pairs. Okay? So for instance, CH4, right? It has no lone pairs, it's surrounded by the same atom, so CH4 would be non-polar. Okay? CH3Cl, it has no lone pair on the central atoms, but it's surrounded by a different atom. CH3Cl would be polar. NO3 minus. This has a charge, so it is attracted to in an electric field, but NO3 itself would be non-polar, even though it has a charge because it's surrounded by the same atoms. CO2, non-polar, surrounded by the same atoms. CO3 2 minus, same thing as NO3 minus. It's an ion, so it's going to attract a polar molecule, but the CO3 itself, we would consider that to be nonpolar. NF3 has lone pair electrons, polar. H2O has lone pair electrons, polar. Okay, now let's go back and talk about why it's nonpolar. So CH4 is nonpolar. Why? Well, each one of these hydrogens has a certain electronegativity value. Electronegativity is the ability to attract an electron when bonded with another element. So these carbons, here's the carbon right here, this carbon is actually pulling on the electrons from the hydrogen a smidge, just a smidge, right? Because it's actually that the carbon-hydrogen bond is considered to be a nonpolar bond itself because it has a small difference in electronegativity. Talked about it in the notes, but I just want to mention that again. So this carbon, get back to this carbon is pulling the electrons from each one of these hydrogens. But since it's all the same, it's balanced. Think about vector forces, right? So I'm going to draw a simple one here. So here's a vector force, here's a vector force, here's a vector force, and they're all the same, right? They're all the same. They're 120 degrees. That means all three of these forces add up to be 0. There is no net force. Same thing here. Since all of these are balanced, there is no net movement. Now let's go back down to the CH3Cl. Here's carbon again. Here's hydrogen, hydrogen, hydrogen. But this time we have this chlorine. Well, chlorine is pretty electronegative, and that chlorine is actually pulling on the electrons from the carbon. And since there's nothing to balance this chlorine, there's nothing around that's going to balance that, the electrons move towards the chlorine, which makes it a polar molecule, right? So this portion of the molecule would be negative, this portion of the molecule would be positive. NO3, if we just look at NO3, I know it has a negative charge, so that means that it is attracted to a polar molecule and vice versa. But if we're looking at just NO3, all three of these oxygens are pulling with the same amount of force. Nonpolar. Look at CO2. Oxygen's pulling, but it's pulling with the same amount of force. So go back to your idea of the force vectors. Here's two force vectors of the same magnitude. Let's say they're both 1 Newton in completely opposite direction. There is no net movement. Skip on down to NF3. So now what we have with NF3, and I'm going to draw it a little bit different just because it's easier to see two-dimensional, is here's the nitrogen, here's the fluorine, Here's another fluorine. Now, we know that those, so it's pulling it like that, we know that those fluorines are pulling with a great amount of force, and there's nothing to balance it, right? So now, there's the other fluorine. It's still nothing to balance it. So that means the electrons are going to move toward those fluorines. That's going to make it a polar molecule. And finally, if we look at water, that may be the simplest to look at. There's the oxygen. Oxygen is typically red when you're doing Lewis, or when you're playing with models. Hydrogen is usually white, so I'm going to make it white. So the oxygen is pulling the electrons. Oxygen is very electronegative when compared to hydrogen. So that oxygen is pulling the electrons. There's nothing to balance out that pull, which means those electrons are going to move. That oxygen is going to then get a partial negative charge. These hydrogens are going to have partial positive charge. So this is actually a partial -2 charge, but it's definitely polar.